And we're back. Welcome back and happy Thursday. Today, we will continue on with some important information about probabilities and get into Bayesian versus frequentist considerations. And so the reading is still the same as last time. The PDF is on the course Blackboard site. The midterm is due the 20th of October, this Tuesday at 4:30 p.m., where you will be giving each talk on the paper that was assigned, Comparative Analysis of Nonlinear Dimensionality Reduction Techniques for Breast MRI Segmentation. So last time when we met, we talked about probability of filtering as a way of motivating so-called conditional probabilities, and semantically discussed it as a filtering probability that changed or limited or reduced the universe of consideration, namely the denominator of the proportion for your probability. And so we use a balls and bins construct and showed that when you have new information, i.e. the tennis balls from bin 5 were the only ones added to the bag, that changed your denominator from 20 balls to 5 balls. And so this had the result of increasing the probability doubling from the unfiltered version or unrestricted version of the probability. And so when we are getting to conditional, we motivated that probability of A given B in terms of the restricted probability for B in our denominator and the events common to A and B, that intersection. And so then we also discussed Bayes' rule, a way of allowing you to change the condition variable, and you can effectively evaluate one condition even though you have not observed that condition. You weren't given that condition, given A. And so we did this Bayes' rule and gave an example of Bayes' rule using airplane arrival and departures, and we showed that we could arrive upon the same result for probability of D given A, whether we did it directly using conditional probability definition, or if we did it through Bayes' rule, we get the same 93.75% probability. So let's go forward. And when we think of a probability expression P of A, functional form is the probability of some event. But you think about it, what actually is A? Well, let's consider an expression. It will rain tomorrow. That's either true or it's false. And so necessarily our probability is a number, real number, on the closed interval between 0 and 1. And a probability of the event 1 means A will definitely occur, or you observe it. A probability of 0 means that A definitely will not occur. And so we look at probability that A does not occur, not A. That's the probability of 1 minus the probability that A occurs because of this law of total probability. We can introduce more definitions. A so-called discrete random variable, big X, takes on values little x. And a discrete random variable is one whose values are either finite, like 1, 2, 3, 4, 5, or countably infinite. You can draw a one-to-one correspondence between the values random variable x can take on and the natural numbers. And so all of the values belong to a set, and we call this set X, and the probability of a given event of little x belonging to some big set, we write for that random variable probability that random variable x takes on or equals little x. We can also write this in functional form, P of x, and we use that as shorthand for saying random variable big X takes on value little x. And so this function P, our probability, is called a probability mass function, or PMF. And so this PMF has a range on the closed interval between 0 and 1. And it just so happens, law of total probability says, if you add up all of those discrete values your random variable can take on, add up the probabilities, that's equal to 1, our law of total probability. So here are some example PMFs, our support set consisting of all of the values that random variable x can take on. In this case, in this example, 1, 2, 3, 4, 5. We could have one type of probability mass function. We see here on the left, that's so-called uniform. You have equal probability, 0.2, associated with each one of these outcomes, 1, 2, 3, 4, 5, 6. And so this probability mass function is called a mass because you can imagine these weights, these probabilities, as being masses, and as such, they're going to exert a weight due to gravity, a force, which is the weight forces due to gravity, on that acting on that mass. And so we also have another type of mass function. This is a degenerate case. We have what's called a point mass. All of the probability mass, all one of it, is concentrated on a single element of the support set. And so here we have uniform equal probability mass at each point, and degenerate, we have all the mass, so-called point mass, all the mass, probability mass at a single point. So let's take a look at some governing properties of all probabilities. These are the so-called Kolmogorov axioms. And now, in order to be a proper probability, your function has to satisfy the Kolmogorov axioms. And there are 3 of them, along with a number of axioms. And so the first one says that the probability is a real number, and it's greater than 0 for all of the events drawn from the sigma algebra over your set of observations, your sample space omega. Now, the sigma algebra, the densest or biggest one, is the set of all possible subsets. So what this says is that the probability of an event or subset of possible events is always non-negative. The second Kolmogorov axiom says that the probability of all of the outcomes, our sample space, will always be 1. And therefore, there are no events outside the sample space. This is sometimes called the law of total probability. And that law of total probability, consequently, is what gives us the probability that not A is equal to 1 minus the probability of A. And the reason for that is if you have 2 events, A and not A, well, they union, A union with not A, is equal to the entire sample space. And the probability of a sample space is equal to 1 because all of the events that comprise the sample space is going to be 1. Okay, so this says the probability of the sample space is always 1, and therefore there are no events outside of the sample space. And this last Kolmogorov axiom, the third one, this is sometimes called sigma additivity. And what it says is it gives you a scheme for how you build probabilities for complex events. It says if you have a sequence of disjoint events, so that means for any 2 events, EI and EJ, their intersection is equal to the empty set. So they're independent and therefore non-overlapping in the Venn diagram, if you were to depict them in the Venn diagram. So if you have a set countable sequence of disjoint events, the probability of their union is equal to the sum of the individual probabilities. So that means, let's say if you have your sample space omega, and you have some event, and that event is carved up into pieces, if those pieces, let's say that's event A, if those pieces are disjoint, then the probability of A, which is equal to the probability of the union, and let's call this A1, A2, the first piece, the second piece, A3, and A4, is equal to the probability of A1, union with A2, union with A3, union with A4. So if we want that probability, that's nothing more than the sum of I goes from 1 to 4 of the probability of event AI. Okay? And so this sigma additivity says that if you want the probability of a complex event and you can decompose it into a set of non-overlapping or disjoint events, the probability of that decomposition is just the sum of the other probabilities. And so that means that if you have a countable sequence of events, you put them together, you get a complex event whose probability is just the sum of the constituent events. Okay, so what exactly is a probability? We said it's a function, yes, and this function has as its domain the sigma algebra for your observations, so that's the set of all subsets of observations, or the power set of your observations, and it has a range between 0 and 1 on the real number line. And so given that probability function, there are different schools of thought, 2 of them, on how probabilities are interpreted. One is called the frequentist view, And in the frequentist view, you look at the probability, this proportion, as the number of trials in the limit representing the frequency of a given event that occur in the limit as the number of trials that you perform to observe some outcome goes to infinity. And so if your probability P is equal to, say, 0.2 or 20%, that means 20% of your trials will be a certain observation. So that's the frequentist view. Now, the frequentist view says that, okay, well, that means you can't talk about an event that doesn't occur. The Bayesian approach has a slightly different interpretation of what a probability is. A Bayesianist says a probability expresses the degree of belief or confidence in some event. And so this relates to the information and not the trial itself. It talks about what you know to be true or something that could occur. And so, for example, we said we believe that the next coin toss will be a heads or it will be a tail. And we can, therefore, with the Bayesian approach, model events that don't have some long-term frequency. You can say, okay, let's suppose you're a radar, right? You see some blip or some signal on the radar. You can compute the probability of a distance over locations of the target, even though that target is something that isn't supposed to occur very much or not reliably. And so this idea of a Bayesianist says, what do I believe? You can talk about something that doesn't necessarily exist and express some belief that it could exist, which is different from a frequentist that says, how often will it occur? So the two interpret the same probability a little bit differently. Okay, so let's take a look at how you compute these probabilities. And suppose we have two events, A and B, and they are overlapping in the Venn diagram, and we want to take the probability of their union. Well, naively, you might think you just add the individual probabilities, and if you did this, you'd be wrong. And the reason for this concerns that overlap region, which is common to A and B. Now, if you take the probability of A and add it to the probability of B, this intersection region, A and B, that's counted twice. One copy is in the A when you add that, and another copy is in the B. And so, of course, there's a problem there. You need to fix it. And how you fix it, like many things in mathematics, you just kind of correct for it. And so how you fix this is by subtracting one of those copies of this doubly counted intersection region. And so if you don't know if two events are overlapping or not, you use this as the recipe for taking the probability, computing the probability of the intersection. That's the probability of one event plus the probability of another event minus the probability of the intersection, and that removes that doubly counted intersection region. Now, certainly if they don't intersect, the probability of the intersect region is going to be 0. So this works in general. So what happens if we have a three-way intersection? We have events A, B, and C, and we want the probability of their union. Well, we add probability of A to probability of B, probability of C. And if we do that, of course, in the same fashion, we're double counting the intersect region between A and C, the intersect region between C and B, and the intersect region between A and B. And so therefore, we want to remove those intersect regions because they're multiply counted. So we're going to subtract off the intersect region between A and B. We're going to subtract off the intersect region between A and C, and then we're going to subtract off the intersect regions between B and C. Now that takes care of the double counted part, but the problem here is this three-way intersect region. When you subtract out A and B, you're removing one copy. When you subtract out A and C, yeah, you're removing this intersect region between A and C, but you're also removing another copy of the three-way intersect region. And then when you subtract off this B intersect C, you're removing that third copy, so that leaves a hole, right? That hole is right here in the center, and that corresponds to A intersect B intersect C, that region, that's the three-way intersection region overlapping between events A, B, and C at the same time. And so how do you fix this up? You add it back in again. So here you have double counted two-way intersect regions and three copies of the three-way intersect region. You subtract out the double intersect regions. You end up adding back in that single copy of the three-way intersection. And this works also in the case if these events are non-intersecting, because any non-intersecting events, the respective probability of the intersecting region is going to be 0. Okay, so you sum the probabilities, you fix up the doubly counted pairwise overlap, and then you add back in that triple overlap, which was removed completely. Okay, so joint probability. When we talk about two events, A and B, we write the joint probability sometimes as A and B, but compactly notation in the literature, when you read this, you'll see probability of A, comma B. And so we talked about from our definition of conditional probability, we did a little algebra, and we got a definition for what the joint probability of A and B is probability of A given B times probability of B, which we said was the product rule of total probability. And we also then talked about this idea of vectors of random variables. Now, for vectors of random variables, we can take a joint distribution, probability between the ANDing of multiple random variables, and we can coerce that into probability of a single variable, the so-called marginal distribution. And how we do that is we take our joint distribution, probability of A and B, and we sum for all instantiations of one of them. And so in this case, if we want the probability of A isolated, we have A with the first value of B plus probability of A with the second value of B plus A with the third value of B, and so forth. And so that's exactly what marginalization is doing. Okay, so here we have probability of A as the marginal from some joint probability between A and B. We apply the product rule, and so we rewrite this probability of A and B, that joint distribution, as probability of A given B times probability of B, and then we instantiate that summing for each value that random variable B can take on. Now, this is sometimes called the sum rule of total probability. And this looks a little bit like the B-slice that we talked about. And so we have a very powerful construct called the chain rule, and we can arrive upon the chain rule using our product rule. And this product rule we can think of as being a factorization of a joint distribution. And at the outset, when we first talked about that, we said that A and B can be single random variables, or they can be vectors of random variables. So let's look at that. So here, compactly, we can write the probability of D many random variables from the same distribution as x1 colon D. So that's the same as the joint distribution of probability of variable x1 and variable x2 and x3 and x4 and x5 up to and including xd. Now, of course, these can be samples from some measurement in time, or they can be different variables altogether. We're just indexing them with this integer to represent a particular random variable. Okay, so we have this vector, and now what we're going to do is we're going to imagine x2 through xd as if it were one variable and x1 if it were another. Again, when we talk about product rule, we can use single random variables, or we can use vectors of random variables. So now we're going to rewrite this using the product rule. We say the product rule of x1, x2, and x3 up through and including xd, that joint distribution, or the ANDing of each one of these d many random variables. We can write that using product rule as the probability of the first variable, x1, given x2 through xd times the probability of x2 through xd, right? So now then we can take this second factor, probability of x2 all the way through xd, and we can now apply the product rule for that. So if we do that, we peel off each one of these variables going from left to right, and we rewrite that using the product rule yet again. And so in that case, we have x2 as one random variable, and then we have a vector x3 through xd. So we rewrite that using product rule as probability of x2 given x3 through xd times probability of x3 through xd. So we keep doing this again and again and again, and eventually we get probability of xd minus 1 comma xd, and we apply the product rule again, probability of xd minus 1 given xd times probability of xd. And so we bottom out because there are no more variables for conditioning, because this is just a single variable probability, a marginal distribution. And so you can think of this successive application of the product rule as factoring this joint distribution as a product of a bunch of conditional distributions. And so literally, we can write this joint distribution as this distribution times that distribution times that distribution times this distribution times this distribution. And so there's more than one factorization. We chose to use the variables in order from left to right, but you could pick the middle one, say x3 given x1 through x2, x4, and xd. And you could do the chain rule that way. And so one of the things that we'll talk about when we discuss Bayesian networks is these Bayesian networks encode dependencies between variables, encoding a particular factorization. And these factorizations are important because it's really, really hard to marginalize when you have a really big vector of random variables. And we talk more about that in depth when we get to the segment or the module on Bayes' rule. Okay, and so on Bayesian networks. And so Bayes' rule, we said before, is probability goes or derives from conditional probability. Conditional probability, there's the definition, probability of x given y is probability of x and y over probability of y. And so this probability of x and y, we can apply the product rule and call that y given x times probability of x. And then we can also take that denominator and we can treat it as a marginalization over the joint distribution. And then we can take that denominator and we can apply the product rule again to use that sum rule form. And here's our full expression for a Bayesian network, for Bayes' rule. And so we have the probability of x given y is equal to the probability of y given x times probability of x over this denominator, which is just this sum for all x, probability of y given x times probability of x. And as you can see here, we have given y for the expression we want, but here we have given x, here we have given x, here we have probability of x, probability of x. So we never observed anything about y. The only observation y is what we're calculating given an observation y, but we're doing it in terms of observations, things that are given for or about x. Okay, and so here we have a classifier, generative classifier, and with a generative classifier, we're modeling the distribution that generates the data. And so we can take that generative classifier and we can factor it to make it easier to construct. And so here, one of the classifiers we can build, we say one of our attributes here, we have a feature vector, x, and x can consist of some vector of observations, x1, x2, up to and including xd for our d-dimensional feature space representation. And then our class label is another attribute, y, and y could be like maybe dog is +1 and cat is -1, or it could be some category and so forth. And so what we're doing when we build a classifier, we're saying what's the probability of a certain label or category given your feature vectors. And so applying Bayes' rule, we have that's equal to the probability of a vector given the class label times the probability of a class label. And then our denominator here is just the probabilities of the vector given the class labels times weighted by the probability of the class labels. And so the interesting thing about this, we have different names for these components. Here, the left-hand side that we're using Bayes' rule to calculate is called the posterior distribution over the class label. It says what are the class label probabilities given certain feature vector instantiations. Now the numerator on the left-hand side, that's called the data likelihood. What's the probability of certain features given the class label? And so here, if you have a class of dog, the color is going to be different. Like we had in the image clustering example, the distribution of colors is going to be different if you have apples, if you have pineapples, or if you have those dogs. And then the prior distribution, those are the relative proportions of each one of the classes that we have. And so we had a 33% of our data were images of dogs, 33% were images of pineapples, and 33% were images of apples. And so this prior distribution is over class labels, and it expresses the proportion of your data from each one of the categories. And now this denominator is called a normalization factor. Its only job is to make sure that this right-hand side of the expression is a proper probability and it satisfies total probability and obeys Kolmogorov's axioms. And so when we compute a generative classifier or probabilistic classifier, all we're doing is coming up with an expression using things we can calculate from our data, the things on the right-hand side of this Bayes rule, to compute the posterior distribution over class labels. And so you evaluate this for each one of the class labels given an input feature as described, or object as described by its feature vector, and then you evaluate all those probabilities for each one of the class labels, and then you pick the class that has the largest associated probability, the largest associated posterior class label distribution. And so this is a generative classifier, and it's immensely powerful and used for a lot of applications, including things like spam filters. And so one of the things you can do is directly fit this class posterior. You fit the probability function to your data for the likelihood, and then you select the class label whose posterior probability has the most mass, i.e. has the greatest probability. All of these quantities you can compute from your data. The prior you can compute from your data. Normalization factor can compute from your data. The likelihood, you just pick a distribution, you can fit it to your data, or you can do it by counting. All of this you can do from your data, use it to compute the posterior, and you output for your probabilistic classifier that prediction associated with the highest probability mass. Okay, so with that, that's all I had to say. It was relatively short today. Again, the midterm presentations will be on Tuesday's class. I look forward to seeing your presentations of the paper. Please make sure you keep it to 15 minutes because we'll be able to fit it in the class time. As usual, please stay healthy, stay safe, and I will see you all on Tuesday.